Hello everybody, this is Muhammad Abu Ghanem, chemistry teacher at Sharjah American International School, Sharjah campus. And today I'm going to cover an introduction of AP chemistry or advanced placement chemistry. So let's get started. First of all, what is chemistry? Chemistry is the branch of science that studies the composition, structure, changes, and the properties of matter. Now, what is matter? Matter is anything that has mass and takes up space. Everything around us is a matter, including things that we cannot see such as air and the microbes. However, light waves, sound waves, radio waves and the magnetic fields are not matter because they don't have mass and they don't take up space. Mass is a measure of the amount of matter, which is measured by kilogram unit, which is different from weight, as the weight is the pull of gravity on an object, or it's a measure not only the amount of matter like mass, but also the effect of the Earth's gravitational pulls on that matter, and it's measured by Newton unit. Weight can change from place to place because the force becomes less as we move away from the Earth's surface at sea level, but mass is constant everywhere. Now, what about volume? Volume is the amount of space occupied by an object. Volume can be measured by many units, such as liter, cubic decimeter, milliliter, and cubic centimeter. And 1 liter is equal to 1 cubic decimeter, while 1 milliliter is equal to 1 cubic centimeter. And to equalize between these units, we have to know that 1 liter is equal to 1 cubic decimeter, which is equal to 1000 milliliter, which is equal to 1000 cubic centimeter. Matter has 4 states: solid, liquid, gas, or plasma. Atom is the basic building block of matter, or it's the smallest building unit of an element that maintains the properties of that element. We have more than 100 different kinds of atoms. So, what is element? Elements, they are pure substances that cannot be broken down by chemical means into simpler and stable substances. And elements contain only one type of atoms. Elements could be monoatomic elements, polyatomic elements, and allotropes. Monatomic elements consist of unbonded identical atoms, such as Fe iron, Al aluminum, Cu copper, and He helium. And mono, it means one. Polyatomic elements consist of several identical atoms bonded together, and the prefix poly, it means many. Polyatomic elements can be diatomic elements, such as hydrogen H2, oxygen O2, bromine Br2, fluorine F2, iodine I2, nitrogen N2, and chlorine Cl2, which can be shown here in the periodic table with the black boxes. We can observe that each one of these elements consists of 2 identical atoms. Polyatomic elements could be others, such as phosphorus P4 and sulfur S8. Allotropes, they are different forms of the same element in the same state of matter. For example, we have oxygen. Oxygen has 2 forms: oxygen gas, which consists of 2 identical oxygen atoms, and ozone, which is located in the stratosphere. Ozone consists of 3 bonded atoms of oxygen, O3. Another example of allotropes is carbon. Carbon can be elemental carbon, C, graphite, C3, diamonds, C5, or buckyball, C60. A molecule is a neutral group of bonded atoms, or it's the smallest unit of an element or compound that maintains the properties of that element or compound. This table shows us the description, chemical symbol, model for atoms or molecules. One oxygen atom, which is O, this is the chemical symbol, and it can be represented by a model or one ball. One oxygen molecule, O2, and those are two identical atoms that can be bonded together to form one oxygen molecule. Two unbonded oxygen atoms, 2O, they are two separate balls, and one phosphorus atom, P, it's like only one rectangle. One phosphorus molecule, P4, they are four rectangles that are bonded together, and the four unbonded phosphorus atoms, which is 4P, they are four separate rectangles and they are separate from each other because there is no bond between them. Elements may consist of either molecules or unbonded atoms. Here we have the periodic table that consists of 118 elements, and each one of the elements is represented by a box, and inside the box we have some information about these elements. Like for example here, the first one we have helium. Helium, this is the element's name. He, this is the element's symbol. 2, it's the atomic number. 4.003, this is the atomic mass. Chemical symbols for all elements appear on the periodic table. Only the first letter is capitalized. The second one is lowercase. Like He, H it's capitalized, E it's lowercase. Sometimes the chemical symbol it's only one letter, and for sure is gonna be capitalized. And in some cases the element symbol is 3 letters. The first one will be capitalized and the other two will be lower cases. This is group number 18 that contains the noble gases, the ones that a complete outer energy level by 8 electrons. That's why they are unreactive and they don't make up compounds. Compounds are pure substances that can be broken down into simpler stable substances, and each compound is made from the atoms of 2 or more elements that are chemically bonded. Compounds contain 2 or more different types of atoms. Compounds have different properties from those of their constituent elements. For example, here we have sodium. Sodium it's a monatomic element which is solid and it explodes in water. And the chlorine Cl2 which is diatomic element and it is poisonous gas. When they react together to form a compound, they form table salts. Table salt it's a matter that has a unique and unchanging chemical composition that is odorless, white, and cubic crystals. So this means the properties of table salt as a compound are different from the properties of their elements which are sodium and chlorine. All samples of a given compound have the same composition by mass. This is called as law of definite proportions, which states that a compound is always composed of the same elements in the same proportion by mass, regardless of the size of the sample or source of the compound. For example, table salt always consists of 39.3 by mass of the element sodium and 60.7% by mass of the element chlorine. The percent by mass it's the ratio of the mass of each element to the total mass of the compound expressed as a percentage. Here we have an example. We're gonna solve this example by using the law of definite proportions. A 550 gram sample of chromium trioxide Cr2O3 has 376 grams of chromium. How many grams of chromium and oxygen are in a 212 gram sample of Cr2O3? The first step is we're gonna get the percent by mass of the components chromium and oxygen in chromium trioxide Cr2O3. To get chromium we have to divide the mass of the element which is chromium 376 over the mass of the compound 550 times 100%. And this is going to be 68.4% of chromium. Subtracting from 100%, which is the total mass of the compound. So oxygen, it's a 31.6%. To find out how many grams of chromium and how many grams of oxygen in this compound, we have to multiply the total mass of the compound 212 gram times the percent by mass divided by 100. It's a 0.684, which is the percent by mass of chromium, and for oxygen it's a 0.316, which is the percent by mass of oxygen. So this compound contains 145 gram of chromium and 67 gram of oxygen. Composition is what the matter is made of. Copper contains of many copper atoms. Water, it's many of 3 sums of 2 hydrogen and 1 oxygen. The properties describe the matter, and it describes what matter looks like, smells like, and how it behaves. Chemistry tries to relate the microscopic and the macroscopic worlds. States of matter are solid, liquid, and gas. And to differentiate between these different states of matter, imagine that you are sitting on a bench, breathing heavily and drinking water after playing football match. You are in contact with 3 different forms of matter. Solid, which is the bench, liquid, which is water, and gas, which is the air. So, the solid state is the form of matter that has definite shape and definite volume. For example, a piece of quartz or coal keeps its size and its shape regardless of the container it is in. The particles in a solid have low energy. That's why they can vibrate, but they cannot move around. The particles in solid are tightly packed together. That's why they are not compressible. A liquid state, it's the form of matter that flows, has a constant volume, and takes the shape of the container. This means definite volume but indefinite shape. For example, water takes the shape of its container. The particles in a liquid have more energy enough to overcome the forces that held them together, and they can vibrate and move around. The particles in a liquid are less closely packed than the particles in solid. That's why liquids are virtually incompressible. A gas state is a form of matter that not only flows to take the shape of its container, but also fills the entire volume. A gas state doesn't have definite shape or definite volume. For example, a given quantity of helium expands to fill any size of container and takes its shape. The particles in a gas have the most energy. That's why they can vibrate and move around very rapidly and freely. The particles in a gas are far apart because the significant amount of space between the particles. That's why they are compressible. There's a difference between gas and vapor, because sometimes we mix up with those two concepts. Gas refers to a substance that is naturally in the gaseous state at room temperature, such as hydrogen gas, while vapor refers to the gaseous state of the substance that is solid or liquid at room temperature, such as a steam or water vapor. Changes in a state of matter. A change of state is a physical change of a substance from one state to another. Like here, for example, we can change from solid to liquid and from liquid to gas and vice versa. To change from solid to liquid, it's called as melting process, and from liquid to gas it's called as boiling process, and from solid to gas directly it's called as sublimation process. From liquid to solid it's called as freezing. From gas to liquid it's called as condensation, and from gas to solid directly it's called as deposition. And during changes in state, the energy will be changed by increasing or decreasing. Now let's classify matter. Matter can be classified into pure substances and mixtures. Pure substances or chemicals have a fixed composition and fixed properties, and they have a single chemical formula. Pure substances can be classified into two main groups, which are elements and compounds. Elements such as iron as monatomic element, nitrogen as a diatomic element, and sulfur as a polyatomic element, and uranium. Compounds such as water H2O, sodium chloride NaCl, and nitric acid HNO3. Mixtures can be classified into two main types: homogeneous mixture or solution and heterogeneous mixture. In homogeneous mixture, sample has same composition and the properties throughout, and evenly mixed at the particle level, such as salt and water. And alloy is an example of homogeneous mixture as well. Alloy is a mixture of metals that cannot be distinguished between the components, as the homogeneous mixture always has one single phase. We have many examples of alloys, such as bronze, which is a mixture of two metals, copper and tin; beer, which is a mixture of lead and tin; and the brass, which is a mixture of copper and zinc. The second type of mixture is heterogeneous mixture. Heterogeneous mixtures are different compositions and the properties in the same sample, and they are not evenly mixed, such as salad and raisin bran. Heterogeneous mixture can be classified into two main types also, which are suspensions and colloids. Suspensions are heterogeneous mixtures that containing particles that settle down left undisturbed, and they can be separated by filtering. Particles over 1000 nanometer in diameter to 1000 times as large as atoms, molecules, and ions form suspensions. One example for suspensions is like the soil, which is a mixture of substances including small rocks, decomposed animals, and plant matter. More examples of suspensions such as paint and the snow globes. The other example of heterogeneous is colloids. Colloids are heterogeneous mixtures of intermediate sized particles between 1 nanometer to 1000 nanometer in diameter, and they don't settle out or can be filtered by filtering. An example of colloid, it's like milk. Milk doesn't appear to be a mixture, but milk is composed of fats, proteins, milk sugar, and water. If you can see milk under microscope, you can see lipids or fats that measure from 1 to 10 micrometer in diameter, and regular proteins particles that are about 0.2 micrometer wide. So this is the chart for classifying matter. Matter can be classified into pure substances or chemicals and mixtures. Pure substances can be classified into elements and compounds. Elements can be classified into monatomic elements, polyatomic elements, and allotropes. Compounds can be classified into ionic compounds and covalent compounds. This is by the way that the electrons are shared, gained, and lost. Mixtures are heterogeneous mixtures or homogeneous mixtures. It depends on the way that the substances are mixed together, if it's smoothly or not. Now, to separate mixtures, we have to involve some physical means or physical changes. No chemical reactions are needed because, as we said before, all substances are physically combined, not chemically combined. The first way to separate between the substances in a mixture is sorting. This is by defining the sorts of the substances. This is with different colors, shapes, textures, etc. The second one is filtration process. The filtration process, it's a physical process that uses a porous barrier to separate a solid from liquid. As the mixture is poured through a piece of filter paper, the solid will be trapped in the filter paper, which is in soluble salt from a liquid. For example, separating sand from salty water. The third process is magnetism. To use the magnet to separate one of the substances. But these substances, one of them at least, must contain iron to be attracted to the magnet and to be separated from the other substance. The fourth process is chromatography. Chromatography, it's a physical technique that separates the components of a mixture dissolved in either a gas or a liquid, called the mobile phase, based on the ability of each component to travel or to be drawn across the surface of the fixed substrate, which is called as a stationary phase. This is how to separate the components of the ink into different colors. The fifth process is by using density. By using density, the one that has more density will be synced and the one that has less density will be float. This is the way how to separate the components of the blood. Here we have the red blood cells that have more or greater density, and the plasma, the one that has less density at the top of the tube. The sixth process, which is distillation. Distillation is a physical separation technique that is based on the differences in the boiling points of the substances involved, used to separate one liquid from a mixture of different liquids that have different boiling points. For example, gasoline, kerosene, fuel oil, and the lubricating oil are produced from petroleum, and they can be separated by the fractional distillation by using the fractionation tower. The properties of matter. Properties of matter can be classified into chemical properties, which are the properties that tell us how a substance reacts with another substances, and the physical properties, which are the properties that can be observed without chemically changing of the substances. And also properties of matter can be classified into two main types: extensive and intensive properties. Extensive properties depend on the amount of substance present, such as mass and volume. Intensive properties do not depend on the amount of substance, such as boiling point, melting point, density, and so on. Here we have an examples for the chemical and physical properties: electrical conductivity, ductility or ductile, malleability, reactivity with water, brittleness, and magnetism. We have to identify which one is physical and chemical properties. So the first one, electrical conductivity. Is it physical or chemical? because it doesn't relate to the reactivity of the substance, if it can react or not, so it's a physical. So the first one is physical. The second and third one, ductility and the malleability, they are physical substances that can be observed or measured. That's why they are physical. Reactivity with water, for sure it's a chemical. Brittleness and the magnetism, both are physical, that can be observed and measured as well. Density. Density, it's how tightly packed the particles are. Density is equal to the mass over volume, or D is equal to M over V. For example, density of water, it's 1 gram per milliliter, or 1 gram per cubic centimeter, because as we said before, milliliter is equal to cubic centimeter, so they have the same value, which is 1. The density of a liquid or solid is nearly constant, no matter the sample's temperature, unlike density of gases, which is highly dependent on temperature. Let's suppose that we have 15 gram of ethanol, which has a density of 0.789 gram per milliliter. What's the volume of ethanol? D is equal to M over V. And by using the crossing process, V is equal to M over D. What is given here is the mass, which is 15 gram, and the density, which is 0.789 gram per milliliter. So let's substitute by these values. So this means V is equal to 15 over 0.789, which is equal to 19 milliliter. Scientists add prefixes to the base units. This task is made easier because the metric system is a decimal system, a system based on units of 10. The prefixes are based on the factors of 10 and can be used with all SI units. Like for example, giga 10 to the power of 9, mega 10 to the power of 6, kilo 10 to the power of 3, deci 10 to the power of minus 1, centi 10 to the power of minus 2, milli 10 to the power of minus 3, micro 10 to the power of minus 6, nano 10 to the power of minus 9, pico 10 to the power of minus 12, and femto 10 to the power of minus 15. And each one of these prefixes has its own symbol. This is the one that we use. So this is, here you have all of these prefixes, and now they are completed. And to remember those prefixes, we have something it's called got from giga. So it's got my cat that cannot miss midsummer's no pants Friday. This is to remember the prefixes. Now the significant figures. We have some rules to find out how many significant figures do we have. First of all, zeros appearing between non-zero digits are significant. Like for example, 87009 kilogram, for example. This means it has 5 significant figures because double zero, it's between 87 and 9. So it's 87009. It's an example. Zeros appearing in the front of all non-zero digits are not significant. Zeros at the end of a number and to the right of a decimal point are significant. Zeros at the end of a number but to the left of a decimal point may or may not be significant if a zero hasn't been measured or estimated but is just a placeholder. It's not significant. A decimal point placed after zeros indicates that they are significant. So all non-zeros are significant. Zeros might or might not be significant. This is to think about it. We're gonna use the box and dots method to determine the significant figures in a given quantity. So this means we're gonna draw like a box on the significant figures. We have like a mission here. The first one is identify the leftmost and rightmost non-zeros. Draw a box around these and everything in between. everything in the box is significant. Nothing on the boxes left is significant, maybe on the right. If there is a decimal point anywhere, the digits on the boxes right are significant, otherwise no. So here we have some numbers and we have to find out the significant figures. We have 80.0, this is the one on your left hand. So how many significant figures for the first one? 80 or 80.0. So this is correct it as 3. As we said, the zeros here, they are on the right of the number. The next one here we have only 2 significant figures because the zeros are on the left of the numbers. The significant here, they are correct, they are 6, as all zeros between the numbers like 13, 0, 0, 4, so they are significant. And the last one, which is 0, also it's included as a significant figure because this is on the right side. And the next one, we have only 3 because 3, 0, 4, 0 between 3 and 4, so they are 3 significant figures, and 0, 0, 0, they are not included as significant figures because they are on the right side. And for the same, the next one here we have only 3 significant figures, 9, 4, 4, and the 2 zeros on the right side, they are not accounted. Here we have only 1 significant figure as we don't have any decimal on the right side. There are 5 significant figures as we have 3 numbers, 1, 2, 4, and after decimal we have 2 zeros that can be accounted as well. Here we have 3 significant figures, 2, 5, and the 0 after 5, they are 3 significant figures. In scientific notation, the exponent has no effect on the number of significant figures. So let's see. Here we have only 3 significant figures, which is 1, 4, and 0. 3 significant figures, 5, 0, and 6. 4 significant figures, 7, 1, 2, 0. And finally, only 2 significant figures, 7, 2, as we have discussed before.